So good afternoon, everyone. Thank you for coming. This is the last distinguished speaker we have for the semester, Professor Pep Español from the National Distance Learning University in Madrid. So Professor Español got his PhD from UNED in condensed matter physics. And then did a postdoc at Cambridge University. And then he went back to UNED, where he's been ever since. He works on condensed matter physics with specialization in coarse-graining, statistical mechanics. He did a lot of work on dissipative particle dynamics, where he has made a number of contributions. And today he's going to tell us about the application of these coarse-graining methods to something a little bit different that he just completed. So I'll let him tell us all about it. Thank you.
Okay, thank you very much for this kind introduction. Yes, I will be talking about something which is at my heart, which is the theory of coarse-graining and a particular application of that theory to a very old problem, which is how free solid bodies move. And this may have applications from the micro nanoscale, where you have this is recent work where you have a small object that may levitate and rotate, and depending on the shape of the body, you will have different spectra, and you can recognize the objects from the spectra. But of course, it also applies to more everyday objects like tennis rackets, or to physical objects like asteroids and satellites and things like that. The problem was solved almost 300 years ago by Euler, 1736. So the question is what to do next after these 300 years. There are a couple of questions that I would like to focus on, and this will be the subject of the talk. So this is the outline. I will present the background of Euler's equations, how they are derived. Then I will talk a bit about the theory of coarse-graining that I will use to generalize Euler's equation to include dissipation. And then I will consider the limit when thermal fluctuations are not important for sufficiently large bodies, and also the case where fluctuations are important. And at the very last, I will talk about what happens when you have one body in the presence of a gravitational field. So first, a bit of a background. Euler took 3 steps to obtain his equations of motion for a body. He assumed that the inertia tensor can be diagonalized. Then he assumed that in the absence of external torques, angular momentum is conserved. And finally, he made the crucial assumption of a rigid body, that the distance between the particles are constant. And from that, he obtain the famous Euler's equation that are written here in a particular notation. So I'm going to present a sketch of the derivation of Euler's equation, mainly to introduce the concepts and the notation. So the inertia tensor is a tensor which is constructed from the positions of the particles in the body, and that somehow describes how the mass of the body is organized around the center of mass. It is a symmetric tensor. It's positive definite. It can be diagonalized, and this was the first step of Euler, with the help of an orthogonal matrix, a rotation matrix. The rows of this matrix, this equation tells us that the rows are the eigenvectors of the inertia tensor, And the diagonal elements here are the eigenvalues. The eigenvectors of a symmetric matrix form a basis of the system, which is called the principal axis of the body. And here are denoted with these colored lines, green, red, and blue. The rotation matrix, it's an object that has 3 degrees of freedom. You can choose, as Euler did, the Euler angles, or as in this work, we choose the exponential representation of the rotation matrix in terms of what is called the attitude parameters. Sometimes this is also called the Euler vector, different from the Euler angles. But essentially, you construct the cross product matrix, which is this antisymmetric matrix that has only 3 independent degrees of freedom. With this matrix, the exponential is an orthogonal matrix automatically. So these are the variables we are going to use to represent the rotation, this attitude. Now, next concept is the angular velocity. The angular velocity, it's a kinematic quantity that it's obtained from the derivatives of the rotation matrix. The rotation matrix in general depends on time because the body moves. So you take the derivative, multiply with the rotation matrix itself, and this produces, because the matrix is orthogonal, an antisymmetric matrix given by the cross product matrix. And the 3 values in this cross product matrix are the 3 components of the polar vector, which is the angular velocity. The angular velocity somehow tells you how the object, what is the rate of change of the orientation. And in fact, you can show that the time derivative of the orientation is given directly in terms of the angular velocity. And there is a kinematic matrix that depends on the orientation. Next concept is the spin velocity. The spin velocity is obtained from the angular momentum S. In this particular way is the inverse of the inertia tensor times the angular momentum. So this allows you to express the angular momentum as the inertia tensor times the spin velocity. Now, the important thing to retain, which I was not aware before, is that the spin and angular velocities are different quantities. And in fact, you can relate both, this dynamic quantity and this kinematic quantity, with this equation that involves the angular momentum in the rest frame. So R0 is the position of the particle I in the rest frame. V0 is the velocity of the particle in the rest frame. So for a rigid body where the particles do not move in the body frame, this is 0. And therefore, the spin velocity and the angular velocity coincide. And this is the hallmark of a rigid body motion, that these 2 concepts, these 2 different angular velocities, take the same value. Okay, so here goes the sketch of the derivation of Euler's equation. You start with the angular momentum. It's the inertia tensor times the spin velocity. You diagonalize the inertia tensor. Then you define the action of the rotation matrix on the spin velocity as the components in the body frame. And then you take the time derivative of this quantity. The time derivative of the angular momentum is 0 because there are no external torques. We are assuming of the motion of a free body. The time derivative, and then you multiply with R. It involves 3 derivatives: the derivative of this object, derivative of this object, and derivative of this object. This gives these 3 terms here. And then you make the third assumption, which is the rigid body, which essentially tells you that the eigenvalues, because the particles do not move, the eigenvalues of the inertia tensor are constant. This is a constant, therefore this term drops from the equation. And the next thing you say is that the angular velocity that came from the derivative of the rotation matrix is equal to the spin velocity. So you substitute this here, and then you get Euler's equations. So an alternative way of looking at the Euler's equations is by considering this kinematic equation that tells you that how the orientation changes with the angular velocity. If you substitute the angular velocity with the spin velocity, you get this equation. And now this is a closed equation for the orientation, because you see the spin velocity is the inertia tensor, which depends on the orientation, times the angular momentum that does not depend on the orientation. So this equation, it's a closed equation directly for the orientation. You don't need to go to the Euler's equation to get directly the motion of the rigid body in the absence of the external torques. Okay, but the problem is that rigid bodies do not exist. If you think of a very rigid thing like quartz, there are thermal fluctuations there, and there is elasticity. We have a sound waves propagating in quartz. So clearly, it's an idealization, it's an approximation, and the question is, from a conceptual point of view, what can we do here, and what implications have? So this was one of my motivations to start with this problem, to look at how you can obtain Euler's equation from Hamilton's equation. On the motion of the particles, how do you get the motion of the body? And to do that, you need non-equilibrium statistical mechanics, which is also known as the theory of coarse-graining. So I'm going to spend the next slides explaining a bit what is the theory of coarse-graining. Well, everything starts with Gibbs, statistical mechanics. Of course, Maxwell and Boltzmann also play a crucial role. But Gibbs introduced several crucial ideas. The fact that you have microstates, which are given in terms of the positions and momentum of all the particles, and those microstates obey Hamilton's equations. And then you have macrostates, or coarse-grained variables, which are functions in phase space, are functions of the microscopic states. He also introduced the notion of ensemble, that you have probability distributions, because you cannot fix the initial, you cannot have absolute certainty about the initial conditions, so you have to use statistical concepts. And he also introduced the notion of entropy related to those ensembles. And therefore, he connected two levels of description, the microscopic level with the macroscopic level of thermodynamics. Then came Einstein in one of his 3 papers of the Annus Mirabilis, the one on Brownian motion. What he did was amazing. He obtained the diffusion equation governing the probability of the position of a Brownian particle microscopically. And this is sorry, I have to look here. He derived the diffusion equation. Apologies. So this is the well-known differential equation for diffusion, and we recognize that D is the coefficient of diffusion. And he gave an expression. He gave an expression for the diffusion coefficient in terms of the microscopic probability of jumps of one of the Brownian particle. This was the first derivation of a transport coefficient in terms of microscopic dynamics. He also introduced the notion of separation of time scales, the fact that you have this evolution of the position of the Brownian particle, which moves as a consequence of many collisions. The collisions are short, are rapid. The motion is slow. So you have this separation of time scales. And it was crucial in his derivation, this notion. Then Green came in this paper from 1952. And what he did was basically to upgrade Einstein's idea on Brownian motion to arbitrary sets of coarse-grained variables. And he said that if, that's a big if, your coarse-grained variables, your selected variables to describe the system macroscopically or mesoscopically, change as a result of many small contributions. So the evolution is smooth with small contributions. Then you can model the evolution of the coarse-grained variables as a Markov, nonlinear Markov diffusion process in terms of a Fokker-Planck equation or a stochastic differential equation. It was not just only a modeling assumption. Green was able to connect, as Einstein did, the explicit form of the drift and diffusion terms of the Fokker-Planck equation with the microscopic dynamics. Swansik, a few years later, obtained the same Fokker-Planck equation by using a technique of projection operators. And since then, Mori, Kubo, Graber, many others in the 60s and 70s of last century contributed to this projection operator theory, which came to be known as the Mori-Swansik theory. But the essence was already given by Green. These projection operator techniques are a way to get the Fokker-Planck equation in macroscopic terms. So this is what the theory tells. The theory tells that the numerical values of your coarse-grained variables that evolve because the microscopic state evolves is modeled, this motion is modeled with a stochastic differential equation, which has always the same structure. It has a reversible part, an irreversible part, a small stochastic drift that comes from the stochastic interpretation of the SDE, in this case is Ito, and a noise term, which is a linear combination of the Wiener process. And the important thing is that all these quantities, the V, the reversible drift, the dissipative matrix, the entropy, all have microscopic definitions. For example, the drift is the conditional expectation of the action of the Liouville operator on the coarse-grained variables. The Liouville operator gives you essentially the time derivative in microscopic terms. So this is a conditional average of the time derivative. It gives you, let's say, the mean motion of the one part of the mean motion of the coarse-grained variable. The conditional expectations are essentially summing over all microstates which are compatible with a given macrostate. The dissipative matrix is given in terms of a Green-Kubo formula. This Green is the Green from that we mentioned before. It is a time integral of a time correlation function of the fluctuations of the time derivatives. This Q is a projection operator, but essentially is the fluctuation, the subtraction of the time derivative from the mean value. Then we have the entropy, which is the logarithm of the number of microstates which are compatible with a given macrostate. And then the noise is given, the amplitude of this noise is given by precisely the dissipative matrix that appears here. And this is what is called the fluctuation dissipation theorem, that the fluctuations are related to the dissipation given by this dissipative matrix. Okay, so that's it. That's the theory of coarse-graining. And the theory is like a black box. You provide the coarse-grained variables, and that's where all the physics enters. All the physics enters in your very selection of coarse-grained variables. And the theory tells you how they move. And this theory is thermodynamically consistent in the sense that you have a second law and you have an entropy increase. You can also show that you have energy conservation. And the theory is pretty universal. Hydrodynamics, kinetic theory, elasticity, all the equations in general, all the equations that are Markovian, the equations where your future is given by the present and not by the past. So equations that involve ordinary differential equations or stochastic differential equations all fall into this structure. Okay, so it's a very general thing. So we are going to use it to obtain a dissipative version of Euler's equations. In the first step, you have to select the coarse-graining variables because the theory is going to tell you how they move, these variables. We choose the dynamic invariance of a body, which is a body which is not subject to external forces or torques, conserve the center of mass, the total momentum, the total angular momentum, and the Hamiltonian. So this dynamic invariance fix the equilibrium state of the system, so we have to retain them. And the second set of variables that we use is the orientation and shape of the body. And this is going to be represented with a gyration tensor. The gyration tensor is related to the inertia tensor, linearly related, but it's more convenient to work with because the resulting expressions are nicer. A gyration tensor is usually used in polymer physics to describe the shape of polymer coils and things like that. It also describes how mass is distributed around the center of mass. It's a symmetric tensor. It commutes with the inertia tensor, and therefore diagonalize in the same principal axis as the inertia tensor. And therefore, we are going to use not the 6 independent components of the gyration tensor, but rather the spectral decomposition. So the orientation of the rotation that diagonalizes and the eigenvalues of the gyration tensor. So 6 numbers again. And those are going to be our set of variables. So we use the orientation and the central moments, the eigenvalues of the gyration tensor, for the orientation and the shape of the body. We want to consider also the dynamics of the shape. And this requires us to include also the time derivative in the list of variables, the time derivative of the central moments. So this is the list of our variables: center of mass, orientation, central moments, the shape, linear momentum, angular momentum, dilational momentum, and total energy. Okay, the building blocks. We have this stochastic differential equation, and we have to compute 3 quantities: the entropy, the reversible drift, and the dissipative matrix. So let's go for it. The entropy. The entropy, the definition is the logarithm of the number of microstates which are compatible with a given macrostate. In the present level of description is this little monster. It involves as many Dirac delta functions as variables we have in our system. And it is interesting that you can do something with that. In fact, if you look at the momentum variables, you realize that you have a kinetic energy term here, which gives you a sphere. It's a quadratic function. And you have the linear momentum, angular momentum, and dilational momentum are linear functions of momenta. So essentially, you have to compute the area, because you are integrating the area of the intersection of a sphere with 3 planes. So geometrically, you can do that. And that explains why you can obtain something relevant out of this monster. In fact, what you can show is this, that the entropy decomposes in 2 terms. One, which is a macroscopic thermodynamic entropy, which is a generalization of Boltzmann entropy. Boltzmann entropy involves the integral of the Dirac delta function of the energy. Now we here also have the rest of dynamical invariants in the system, the center of mass, momentum, and angular momentum. And the important thing is that this entropy depends on the set of variables only through this particular combination in terms of the internal or thermal energy, in which you subtract from the total energy, you subtract the organized forms of kinetic energy, the translational kinetic energy, the rotational kinetic energy, and also the dilational kinetic energy, because this body we are capturing the motions of dilations. And the next bit is this logarithm of a probability. It's the probability of finding at rest a body with a particular orientation, a particular shape, and a particular velocity, dilational velocity. It decomposes in three terms. One that depends only on the orientation. Those are the expressions. Another one that depends on the central moments. And we assume that this is Gaussian. So the fluctuations of the shape are Gaussian. This will produce elasticity at the end. And there's also a Maxwellian in the dilational velocities. Fair enough. We have an explicit, really explicit model for the entropy of a rigid body. The block 2, the reversible drift, of course, the dynamical invariants do not evolve, so this gives 0. And from the rest of terms, you can compute everything explicitly. In particular, this term that gives you somehow the reversible part of the dilational dynamics. It involves a dilational force that has 3 terms. I will discuss this later. The dissipative matrix is a monster again because we have many variables. Many of these vanish because it involves correlation of things that do not move, the dynamic invariants. So at the end of the day, you only have 2 terms here, hopefully. And these are given in terms of green cube expressions that involve the time integral of the correlation function of fluctuations of time derivatives of coarse-graining variable, in this case, the orientation and the dilational velocity. You can go, this is very difficult to compute, but you can play with this transformation to the principal frame and the integrations of momenta, and you can show that this orientational diffusion actually involves the difference between the angular velocity and the spin velocity. So this difference is in the guts of the dissipation that defines this transport coefficient, this orientational diffusion. You can find a more explicit expression in terms of the orientation, and that's it. So the final equations are these ones. Of course, the dynamic invariants are conserved quantity. They do not evolve. You have an equation of motion, a stochastic differential equation for the orientation, for the central moments, and for the velocities of the central moments. And you have a stochastic drift here that it's explicit, and you have the noise here that are explicit. So everything here is explicit. So those are usable sets of equations that you could simulate, because you know everything in these equations. And okay, so we are very happy. But the thing is, what do these different terms mean? So to look at this question, what is the physical meaning of these terms, we will first consider the case where we don't have thermal fluctuations. The body is sufficiently large that they do not play a role. So we keep only the blue and red terms. The blue are the reversible part of the dynamics. The red is the irreversible part of the dynamics. So let's go for the deterministic dynamics. It has this form. The orientation evolves with a term which is identical to the Euler equation, and therefore, and another term which is purely dissipative. Sorry. So those are, this is a generalization of Euler's equation that includes dissipation. And for the shape, it evolves in a very simple way. You have the central moments move with the velocity of the central moments, and the velocity of the central moments are subject to forces that there is a term which is purely convective in the same way as the rho VV term in the Navier-Stokes equation appears. It's just pure convection. There is a term which is gives you idea about centrifugal forces, the fact that centrifugal forces have to affect the shape of the body. And there is an elastic contribution that basically tries to keep the central moments close to the rest value of the central moments. So let's see what happens with Euler's equation written in this particular way. This describes the motion of perfectly rigid bodies. And in particular, it describes a phenomenon that has been popularized on YouTube a lot. There are recently thousands of videos describing this effect. It was discovered by Dzhanibekov, a Russian cosmonaut in outer space. He spun a wing nut, and he saw how it evolved. I'm showing pictures. This is from a space station. If you rotate a triaxial body, you see that it's doing a funny thing. It changes the axis of rotation periodically. This is in a slow motion where you can see it slightly better. Okay. You can see that this also happens on Earth. You have to take a slow motion. Now the wing nut flips as it spins. Okay, until it crashes on the floor. So let's see how this emerges from this Euler's equation. So we are going to numerically simulate these equations, and this is what happens. The body axes are in color. There are smoke that vanishes in time that gives the traces. And you see that it becomes unstable. It's rotating around the intermediate axis, which is unstable, and it flips down, keeps rotating until it flips up and goes on forever. And we can stay watching this forever. We don't have that time. Let's see what happens when we include the dissipative terms in the equations. What happens is this. Again, is rotating around the intermediate axis, which is unstable. It stays there for a while until suddenly it becomes unstable and goes there forever now, which means that it ends up rotating around the major axis. It's a completely different phenomenology. If we look at the dilational kinetic energy here, that gives you an idea of how is this moving. Initially, we set in motion the body. There are centrifugal forces that initiate this oscillation. But then the friction coefficient in the equation damps these oscillations until the kinetic energy, the relational kinetic energy is 0, which means that the body takes a shape as it rotates, which is constant, and which is the result of equilibrating the elastic forces with the centrifugal force. The rotational kinetic energy, initially it also oscillates because, remember, is the kinetic rotation kinetic energy is angular momentum inertia tensor minus 1 angular momentum. The inertia tensor depends on the central moments. So there are oscillations, which are reflected here. But when the body goes to turn around the major axis, it decreases strongly. So in a way, what this is saying is that rotational kinetic energy is reduced, total energy is conserved. And this means that when the body starts spinning around the major axis, it heats up. All this rotational kinetic energy goes into thermal energy of the object. This phenomenon, the fact that you end up spinning around the major axis, is known as precession relaxation. And this is the thing. If Dzhanibekov had waited long enough, he would see the wing knot spinning. If this is the wing knot, not spinning like that and turning back, but rather spinning around the major axis. What is the origin of this precession relaxation? Well, we have an entropy. We have computed the entropy, so we can compute the time derivative of the entropy, use the equations of motion, and check that indeed this is a positive quantity. It increases in time because this is a quadratic term, and this is also a quadratic term. It increases until it gets constant with a maximum entropy, and this can only be when this time derivative is 0 if these terms are 0, which is only possible if the spin velocity and the angular momentum are parallel. But if the angular momentum and the spin velocity are parallel, it means that the angular momentum is an eigenvector of the inertia tensor. It means that the body, because of the entropy increase, will end up spinning around the axis, will align its major axis with the angular momentum. So it's a consequence of the second law, this precession relaxation. Okay, so can we observe this? Because what I have shown is the numerical solution of our equations. Okay, so here is a molecular dynamic simulation of a body, a small body, at different instants of time. This is the rotational kinetic energy. It has a large amplitude here that arises because of the oscillations due to the initial kick that induces centrifugal forces, but the rotational kinetic energy decreases in time. And we see the different times here and different frames. Oops, sorry. But this is, it takes a while, takes a long time to get, but eventually you see that it ends up spinning around the major axis. So yes, this is observable. And in fact, this explains why the vast majority of asteroids observed spin around the major axis. And you know that because you look at the light which is reflected, and it's very periodic. And this can only happen if it's not tumbling. Okay, so let's move now to the stochastic results. When the body is very small, thermal fluctuations become important. And this, remember, these thermal fluctuations are intrinsic. They came because of the motion of the atoms. There is no thermal bath around. These are the equations, the full equations, stochastic differential equations. To see what's going on, it's best to consider first the case when the body is not spinning. So we have a body at rest. The angular momentum is 0. And the orientation equation decouples from the equations of the central moments. And you only have this set of equations. It is a stochastic differential equation. And you can make the following question. You can ask how, because the orientation is something which is difficult to grasp, because it's 3 numbers that define the orientation. But it's much easier to look at the basis, at the principal axis, how they move, no? How they move implied by the motion of the orientation. So you have to use Ito calculus, because the principal axis are the rows of the rotation matrix. So you have to, and you know the attitude parameters in the rotation matrix move. This implies the motion of the central moments. It's you have to use Ito calculus, and you get this equation. So the update of the eigenvector of the principal axis is the vector product of the principal axis vector with the Wiener process. And this is, by definition, something which is well described in the mathematical literature, which is Brownian motion on a sphere. So what this is telling is that a body at rest, if you look at and I can show it here, we have a body at rest. Those are molecular dynamic simulations I'm going to show. And this is the principal axis, and which are unit vectors that the motion describes a random, due to thermal agitation of the atoms inside. It gives an anisotropic Brownian motion on the unit sphere. And it's anisotropic because the body is easier to move in one direction than in others. And eventually I'm showing snapshots at different instants of time, and it really covers all the space. So a body with 0 angular momentum rotates and ends up covering the unit vectors, ends up covering the whole sphere, which is, in a way, is understandable. There's nothing in this body that gives you a preferred direction, so it's going to move around. For Brownian motion, you can, for the Brownian motion of a particle on the sphere, you can prove that the correlation of the position of the vector is decays exponentially. And this is what appears here. This is the correlation as a function of time of the 3 eigenvectors. And the lines are the theory, the crosses are the simulation, MD simulation, and we have an excellent agreement. There is a fit here that allows us to measure the orientational diffusion coefficients. But the decay is exponential. So, okay. Now we can go to the case that we have certain angular momentum. And what we see is a sort of Dzhanibekov effect, stochastic Dzhanibekov effect. Initially, it goes up and down. And if we wait sufficiently long, let me see if I can, okay. After a long time, it's doing that. So it is spinning, trying to spin around the major axis, of course, affected by thermal fluctuations. So it's a stochastic Dzhanibekov effect, but eventually it dies into a precession relaxation. And then to close the loop, we have measured the diffusion coefficients, and now we try to predict the decay of the rotational kinetic energy. And those are the results of the stochastic numerical result of the stochastic differential equation and the molecular dynamic simulations, and they coincide very well. There is a lot of noise because this is a single simulation. It's very, you saw it was jiggling a lot. So we have to take many averages, but it goes well. So I have to. So with this, I would say that we have tested through molecular dynamic simulations the theory, and we can extend it also to the case that we have this body, an asteroid, for example, in our moon, in the gravitational force of the Earth. Just one mention is that you can express the gravitational potential in terms of the gyration tensor through a second-order expansion. And then this allows you, because the potential energy is a function of the macro state that you have chosen, the gyration tensor is in the set of relevant variables, then you can use directly the expression for the entropy in which you subtract for the thermal energy the total energy. You subtract also the potential energy, but the rest of things are immediate. And these are the equations that emerge from this theory. This governs the position, the orientation, the central moments, the momentum. Of course, the forces are purely gravitational. You recognize here the R² force, and also these are the tidal forces that depend on the gyration tensor. And also you have an equation for the shape of the body. Total angular momentum is conserved, but the angular momentum of the body is not. So you have this term here. Now, these equations respect the second law, and therefore you have an equilibrium state. These equations predict an equilibrium state, and the equilibrium state is one in which the body orbiting around the origin of the central gravitational field ends up moving in a circumference at constant speed and orientating in such a way that it offers always the same phase to the origin. And this is what the moon does. It spins at the same rate as it orbitates. So this theory predicts tidal locking. Of course, Newton himself already knew that the origin of tidal, that we only see one phase of the moon, is due to the tidal forces. What this theory predicts is how we reach the equilibrium state. If you simulate that without the dissipative terms, you would get something that would spin forever in an elliptical orbit and doing whatever it does. Only with these dissipative terms, you get this circular and the appearance of a tidal locking state. So the conclusions are here. The original Euler's equations cannot predict precession relaxation. The theory of coarse-graining allows you to obtain the equations that generalize Euler's equations with dissipative terms. They predict the tendency towards equilibrium through the phenomenon of precession relaxation. We have validated the theory through MD simulations. Small bodies display anisotropic Brownian motion, and bodies in a gravitational field evolve due to dissipation towards a tidal locked state. And with that, I conclude. Thank you.
Thank you very much. It's a very nice talk. We have time for questions. Yes.
Thanks for the great talk. Regarding,
I think it's on.
okay, so it's for Zoom, I guess. Okay, so regarding the last thing that you're mentioning about tidal locking, so based on what we currently observe, is there any way just from looking at the current dynamics to back out, like at what point did the moon have, you know, like kind of the evolution of the moon's dynamics over time?
Okay, that's a good question. In principle, there are very precise measurement of the position of the moon, and from that you could, because there are certain parameters in these equations. In particular, there is a diffusion orientation parameter that you don't know what it is. You can compute that from a small body, from MD, but you will not use MD for the moon. So you have to fit those parameters. You could probably, because the moon is receding at almost 4 centimeters per year, you could try to fit this to the observation and try to find the value of the diffusion coefficient, the orientational diffusion coefficient. And in principle, you could retro-predict the evolution. But then lots of things happen indeed, because I mean, the origin of the moon is comes from an impact. This was not a rigid body. It was, I mean, very close to, at very early stages, the moon was very close to the Earth, and probably the second order expansion here was not correct. So this is, it gives you a simplified way of looking at the problem. But physics is much more complicated than this.
So is the recession part also predicted by this?
Yes. If you choose initial conditions in an elliptic orbit, so you have an elliptic orbit, eventually, from pure dissipation, it will go into a circular orbit, and it will spin, offering the same phase. Now I'm trying to generalize this to the case of two bodies, because the moon is tidally locked, but the Earth eventually will be also tidally locked, offering the same phase to the moon. But because the mass differences, this takes much longer.
Questions? Yes?
Yeah. Okay. Wonderful. I like the talk very much. And
Thank you.
I have several questions, but let's start with a couple. The dissipative matrix M, you didn't say, but it's symmetric. It must be symmetric, and it must entail the Onsager reciprocity theorem. Okay. Then you have an expression for the rate of entropy production, which of course is compatible with the principle of entropy non-decrease, so it's non-negative.
Yes. So you mentioned.
I'm getting right. Yeah, you had
Sorry.
So I'm getting to the question, but there is if you remember, there is a theorem by Glanzdorf and Prigogine about the minimum entropy production. So, which essentially would say that if you are in that regime, and that will be the question, you would have, if you compute the second derivative with respect to time, so the rate at which the rate of entropy production moves from off equilibrium towards the equilibrium, in that theory, which would be a near equilibrium theory, that derivative would always have a negative value. In other words, you start with a high entropy production rate, and then it goes down until you go to 0 at equilibrium, or to a certain steady state. But I don't think here you don't have external forces, so you cannot sustain a steady state. But that theorem applies only in the near in what I would call the near equilibrium limit. So my question is this theory somewhere in your assumptions assuming that you are near equilibrium?
No.
Okay.
No. The theory can deal with arbitrarily far from equilibrium situations. For example, Navier-Stokes falls into this scheme. And Navier-Stokes has turbulence, shocks, very, very non-equilibrium behavior. So,
no, but I meant really far non-equilibrium, because Navier-Stokes, in my view, is a near equilibrium approximation, because you assume a linear relation between the stress tensor and the deviatoric part of the strain.
No, but the matrix may be state dependent. So it's highly nonlinear. The dissipative matrix,
Okay.
it's given in terms of a conditional expectation,
Mm-hmm.
and it depends on the state in general. Of course, near equilibrium, it's the viscosity. It's the viscosity at that point of equilibrium. But in general, the theory is
Okay. In that sense, then I'm sure that because that reminds me of my steepest entropy ascent theory that I will tell you later. But in that means that only when you are going to be near equilibrium, you would have the second derivative of the entropy production be negative. Because far from equilibrium, you could have entropy goes up, entropy rate go up and down.
I'm not sure, but I think I made the calculation, and the second derivative of the entropy turned out to be negative.
Does it always?
Yeah, but let me check.
Okay.
Do we have any questions on Zoom? No? All right. So I think we end it here and we can talk some more offline. Thank you very, very much.
Thank you.